The first part of Module 6 discusses circular motion. Welcome to Engineering Physics. As previously discussed that kinematics would have rectilinear and curvilinear motion, Module 6 is all about motion in curves. But let us identify clearly the two methods of having a circular motion. We have spin, which is the motion of an object about its internal axis, just like the rotation of Earth, and we also have orbit, the movement of an object around an external axis. Sometimes we call it revolution. Rectilinear motion is the movement of an object in a straight path, and using vectors we can denote parameters as moving horizontally, moving vertically, or even at a certain inclination. For circular motion, it is the curved movement of a particle due to some force drawing it at some point of origin. Let us analyze the two different types of motion. As learned previously, if the force acts at the same direction with velocity, its speed will increase, whereas if the force is opposite the velocity, the speed will decrease. How about if the force is perpendicular to the velocity? The movement of the object will be circular, and at a certain point A, there will be a force which will draw the object to the center, which we call centripetal force. The velocity will have the same magnitude but changing direction, and we call it tangential velocity. Later on in dynamics, you will find out that besides using the x and y axis to take components, especially for circular motion, there are different axes to consider, one of which is the pair of the normal and tangential components. In the image, the vector r is considered as normal vector and the vector v is considered as tangential. For the force drawing objects to the center of orbit, or what we call centripetal force, there are different factors which we can consider. In the case of a sling which revolves an object by a string, the centripetal force is influenced by the string's tension. With the orbit of the moon around the Earth, centripetal force is influenced by gravity. And the case of a car driven on a curve, centripetal force is affected by the friction between the tires and the road surface. Centripetal force can be computed as F sub c is equal to mv squared all over r, where F sub c is the annotation for centripetal force, m is the mass, as v would be for velocity, and r is the radius of curvature. If we integrate Newton's second law of motion, which is F is equal to m times a, centripetal force can be said to be m times a sub c is equal to mv squared all over r. And cancelling similar parameters in both sides of the equation, we can arrive with a formula for centripetal acceleration, which is a sub c is equal to v squared all over r. The next parameters are the frequency and period. The definition of these two parameters are just interchange and they normally go together. Frequency is the number of revolutions over time, and period is taken as time over the number of revolutions. So incorporating them both, we can say that period is just the reciprocal of frequency. To solve for the angular velocity, we derive the formula from uniform motion. And as explained, distance is velocity by time, which gives velocity as displacement or position all over time. In a circular motion, the distance is taken as the circumference of the circle, and time is the period to make one full revolution. Thus, the formula for angular velocity is 2 pi r all over period t. Let us check the integration of some formulas we just derived. Let's say that the centripetal acceleration is given by the formula a sub c is equal to v squared all over r, and angular velocity is taken as 2 pi r all over t. If we plug velocity into the formula of centripetal acceleration, we get 4 pi squared r squared all over rt squared, where radius can be cancelled out and leaving us with the formula of acceleration as a function of period, a sub c is equal to 4 pi squared r all over t squared. Example 1 is a simple computation to find out the different parameters we just discussed. A 12-kilogram test rocket revolves at a radius of 10 meters. It makes 15 revolutions in 5 seconds. Calculate A, frequency, B, period, C, centripetal acceleration, D. Centripetal force, and E. Speed. Frequency solved as revolutions per time, that would be 15 over 5 seconds, giving us 3 revolutions per second. Period is the opposite, which would be time all over revolution, or 5 seconds per 15 revolutions, giving us 0.333 seconds per revolution. Or, we can also use the reciprocal of frequency to solve for period, that is 1 all over frequency, still giving us the same answer, 0.333 seconds per revolution. Initially, centripetal acceleration is given as a sub c is equal to v squared all over r, but the problem has not disclosed velocity. Thus, we can use the second formula as a function of period, that would be 4 pi squared r all over t squared as a sub c. By placing the digits, we would have 4 pi squared times 10 all over 0.333 squared is equal to 3560.174 meters per second squared. Centripetal force is also presented with an initial formula, F sub c is equal to mv squared all over r. But since velocity is not given, the formula will lead us nowhere. So taking the Newton's second law, we can have F sub c is equal to m a sub c, which then becomes 12 kilograms times 3560.174 meters per second squared, giving us the answer 42,722.092 newtons. And lastly, for speed or velocity, knowing that centripetal acceleration is a function of velocity and radius, we can solve for the velocity as root of a sub c times r, which would be root of 3560.174 times 10, giving us the answer of 188.684 meters per second. The second example deals with circular motion moving horizontally. A 500-gram ball attached to a string moves in a horizontal circle of radius 1.5 meters. Calculate the tension if A, velocity is equal to 20 meters per second, and B, if velocity is just 5 meters per second. If an object is moving so fast in a horizontal motion, the force in the string will focus on the centripetal force, so tension T can be taken as mv squared all over r. And placing the given, we can have 0.5 times 20 squared all over 1.5, and the answer would be 133.33 newtons. On the other hand, if the velocity is low, like for example 5 meters per second, the string will be acted upon by two forces. The horizontal force is still the centripetal force. However, because of the slow movement, a vertical force acts on the string based on the object's weight. If we take these two forces as the components of the tension, then T sub x would be equal to mv squared all over r, or that would be 0.5 times 5 squared all over 1.5, giving us 8.333 newtons, and T sub y as mg, which is equal to 0.5 times 9.8, or 4.9 newtons. Then following procedure in solving for the resultant, we use Pythagorean theorem, that would be the root of tx squared plus ty squared, so it would be 4.9 squared plus 8.33 squared. Take the square root, giving us 9.667 newtons. In case the circular motion will be vertical like the Ferris wheel, note that the weight will be a factor in identifying the centripetal force. If the object is at the bottom, its weight will be adding to the centripetal force. That is why you would find it harder to lift the object up. If the object is at the top, just like for free fall, that it will automatically move down, the object feels lighter, and weight is deducted from the centripetal force. Similar with the horizontal motion for the left and right spots, tension will only account for the centripetal force. Take this for an example. A 500-gram ball attached to a string moves in a vertical circle of radius 1.5 meters at a speed of 5 meters per second. Calculate the tension force at the A, top, B, bottom, and C, midway the circle. Tension at the top can be computed as T is equal to Fc less weight, which when expanded would give us mv squared all over r less mg. Where placing the values, we can get 0.5 times 5 squared all over 1.5 less the quantity 0.5 times 9.8, and we would have 3.433 newtons. Tension at the bottom will have the opposite operation. That would be T is equal to F sub c plus W. And Having it expanded the same as mv squared all over r plus mg would give us our values 0.5 times 5 squared all over 1.5 plus 0.5 and 9.8, giving us 13.233 newtons. And halfway the motion, left or right, we take t is equal to mv squared all over r, which would simply be 0.5 times 5 squared all over 1.5, giving us the answer 8.333 newtons. Continue learning about circular motions with Module 6b, rotational motion.